All right, the first thing I want to do before jumping into the triangle problem is I have a brief announcement before I forget, and that is, oh goodness, that is midterm 2 is currently scheduled for a Friday. I want to say it's like the 5th or the 6th or something on that, and I want to move it to that Monday afterward. I think it was a good thing to give you all the weekend to study, and I think going for a midterm on a Friday is just going to be, it's not going to give you enough time to really think about what we've gone over in practice. So I want to move it to Monday, June 8th. So this is my current plan. If you have any blaring issues, why that is a huge problem, reach out to me via email, and I may not do this if there are enough people who really have a problem. So just something to keep in mind. I think overall it would be better for the class. In fact, this was my original plan, and I realized on the syllabus recently, I think it wasn't written for June 8th. So just a brief announcement. So let's do this. Also, don't hate me too much, but I'm naming it the triangle problem, and I'm naming it that because I made this problem up. So I get to name it. All right. Last year, the test scores of a particularly difficult statistics exam followed a symmetric triangle distribution where A is 51, B is 71, and C is 61. Note these numbers were randomized for every single person's exam, so I'm just going to do my solution with these three numbers. But if you go through your own solution and it doesn't work out, come to me and I can help you go through it with your numbers. So these are all places at the x-axis. So the value at the x-axis here is 51. The value here is 61. The value here is 71. There were two main things to remember when trying to do this problem. And the first is the area under the curve is equal to 1. And this is something that's true for all density curves. And it's something we've talked about a few times with the normal, with the uniform, and with density curves in general. So that was the first thing to remember. And the second thing to remember is to silence my cell phone. The second thing to remember is proportion / probability. Okay. Let's put me on do not disturb. Okay. / probability calculations are equivalent to calculating the area under the curve. Okay, so these are the two main ideas. So the answer to part A, which was what is the total area under this curve, that actually didn't require any calculations whatsoever. It was just the number 1. All right? For part B, what is the height of the curve? Well, I gave you this formula, area equals 1/2 base times height, right? Well, I know what the area is. It's equal to 1. I know what the base is. That's just going to be the length of this right here, which is 71 minus 51. That's the length of the base of the triangle, times the height. Which means that height in this case is 2/20, which is 0.1. Okay. The next one was the first one where you had to do an area under the curve calculation. So what is the proportion What is the proportion of scores we observed at or below 60? So less than or equal to 60. And the first thing you always do with problems like these is you draw a picture. This is 51, this is 71, this is 6. Ooh, what's going on? 61. And I want to know here is 60. I want to know what the area of this right here is. Well, it's actually just like our previous calculation. If we want to know the area under the area under the curve here is just a triangle. So area equals 1/2 base, which is 60. The base right here is just 60 minus 51 times the height, which I gave you in the problem. So is, ooh, well, let's see what this is. If you do all these calculations out, it's equal to 0.405. Okay. Next up is, what is the probability of being greater than or equal to 67? And that again is just the area under the curve, so we draw a picture. '67's around here, and I want to know the area in this upper tail, greater than or equal to. Area is equal to 1/2 the base, which is 71 minus 67 here, times the height, which I gave you in the problem, 0.04. Let's find out what this is. This one is 0.08. Okay. Part E, what is the probability at exactly 61? And this is so the probability at a point is just a straight line, and the area of a straight line is equal to 0. Just like any density point, the probability of a single point is 0. It is only meaningful to talk about ranges of probabilities, because otherwise we can't get our area under the curve calculation. And then part F, we want to throw the probability between 60 and 67. And this is actually just sort of, if this is 60 and this is 67, this is the area in the middle here. But no, we actually already calculated this, it was 405. We already calculated this, it was 0.08 on previous problems. So all you had to do, since total area under the curve is equal to 1, you just take 1 minus 0.405 minus 0.08, which was 0.515. All right, any questions on this problem? So it was supposed to be the tricky problem of the test. The idea was, if you remember these two main things about density curves, all the calculations should have kind of fallen into place. So definitely, if you're still struggling with it, kind of go over this, kind of think about it a bit more, and definitely come to office hours if you have any more questions. All right. So the other one we want to talk about was the least squared regression problem. And this one I'm not going to walk through. The calculations we've already practiced in many different ways, but I did want to make 2 points about it. The first point is that in Excel, you can build a scatter plot, which I taught us how to do. What's the trend? For some people, it was positive or negative, so I'll choose a negative trend, right? And you can have the scatter plot give you the least squared equation and r squared. And I believe some of you did this. Some of you did, you took your r squared, you took the square root of it. And you got r. Then you took r, and you got this. So these are all the correct formulas. The issue is that this number, first of all, this isn't how I taught us how to calculate this value. I wanted you all to use this. Oh my goodness. How can I do not disturb everything and I still get notifications? My goodness. This is not how I told us to calculate this. I would have preferred we use the Correl function in R because that gives us the best precision. The problem with using this r squared, right here is that Excel doesn't give you that many digits. In fact, Excel goes ahead and rounds that value. And when you take a value, when you're calculating B1 and B0, and you round as you go, the error that you accrue by rounding as you go gets greater and greater, and by the time you get to the last number, you're so off that WebAssign doesn't allow you the correct answer. So certainly be very wary of this in the future. This is actually something that came up in our most recent homework, that you should use as many digits as you can and only ever round at the end if it asks you to round at all. So I think a bunch of people got your intercept wrong because of this very reason. You used this number rather than using Correl. And the other thing that happened, I think a few people, they calculated their intercept using this. I saw this a few times instead of this. So they put the correlation here rather than the slope. So that was also something that came up. So definitely don't just assume you had this first problem. Definitely check your answer when you get a chance. All right. So any other questions on these two things? Okay, well, we do actually have a lecture today, so I guess I can go ahead and get started with that. Let us start with chapter 3. So what we have done so far, up into and including the first midterm, we've covered a lot of bread and butter topics in statistics. We've done the squared regression line, we've done sort of common terms, ideas of sampling and population, and then we've further talked about density curves, which are like one of the biggest and most important topics we can talk about in a class like this. So now that we've done statistics, we're going to start talking about the bread and butter topics of probability. And depending on who you ask, statistics and probability are the same field or they're distinct fields. And no matter what you believe, they are certainly fields that use a lot of the ideas from each other. And the more you get into it, speaking as somebody who does theoretical statistics, the more they just seem like the same thing. So today we have an introduction to probability. I think it would be most appropriate for me to write this definition, which is one we've actually seen before, which is the definition of a probability. So the probability of an outcome is the proportion of times the outcome would occur if we observed the random process an infinite number of times. So in this class so far, I've actually kind of mischievously used proportion and probability interchangeably in a few contexts. And the reason that is because a probability is actually a proportion. It is sort of this theoretical proportion that we would get if we were to observe the process over and over again an infinite amount of times. So the quintessential example, which I think I'm about to return to actually, is flipping a coin a bunch of times. We say probability, it's probability heads. With 1/2 probability, you get heads, right? And this is an expression of, if I were to sit here and flip this coin an infinite amount of time until I was super old, what proportion of times would I observe heads? And the answer is 0.5. So it is an expression of infinity, which is it's a little theoretically cumbersome. It's a little hard to think about, but it is the precise definition of what I say when I mean probability. So keep this in mind as we talk about these next things, because I throw the word probability at you a lot, so it's good to keep in mind what it actually means. So let's talk about randomness. A random phenomenon is a situation in which, one, the outcome is uncertain. Did I say certain? That's funny. Uncertain. But two, there would be a definite distribution of outcomes if the situation were repeated many times under identical conditions. Ooh, that is not how you spell conditions, everyone. The more you know. So I'm gonna make a note. Recall a distribution is all possible outcomes and how often they occur. So distribution is something we spoke about before, actually, when we were talking about density curves. And I'm actually going to make, oh, excuse me, I need some of this tea. I'm actually going to make the connection between what I mean by distribution and what I mean by density curves in the video lecture. So something to look forward to. So this is a lot of words. Let's do an example. Rolling a six-sided die. And I'm going to say a fair six-sided die. So no loaded dice here. And I got a picture. This one. So what do we see here? This is the histogram that I would get by rolling a die 20 times and every single time recording what value the die took. So the die can take 1, 2, 3, 4, 5, or 6, right? And according to this, in my 20 tosses, 0.2 or 20% of the time I roll a 1, 0.15 or 50% of the time I roll a 2, and so on and so forth. Okay? Note, when I rolled it 100 times, I still got some variation, but it looks a little less varied than when I did it 20 times. Now if I do it, what is this, 10,000 times? Notice how there's hardly any variation at all. In fact, if I were to say, it looks like they're at about 0.16, just looking at the graph. So what is our random phenomenon here? The random phenomenon is rolling a six-sided die. The outcome is uncertain. I don't know what the value of the die is when I roll it, but I do know that as I roll it more and more, I'm going to see the numbers 1, 2, 3, 4, 5, and 6. So I want us to look at one other thing, which is 100,000. And I do not know who they got to sit down and roll a die 100,000 times, but I feel very bad for them. In fact, that sort of sounds like something a professor would make a grad student do. I'm a grad student, and I've yet to be forced to do something like that, but I have been forced to do very banal tasks. Actually, I'm sure they just used a computer to simulate this. I'm kind of joking, maybe a little bit. So what you see here are the number of times we roll a six-sided die. So n is the number of rolls. And what you see here is the proportion of times we observe 1. Okay? So I rolled it a bunch of times. It looks like on the 5th roll, I saw, oh, I rolled a 1, right? So every single time I roll, I kind of update my proportion. And you can see as we roll more and more, it is getting closer and closer to kind of evening out. Did I say that right? Whatever. And it's evening out at around 0.16. So it's looking like these two graphs right here are saying about the same thing. If we do this over and over and over again, our probability, or our best guess of the probability, is getting closer and closer to 0.16, which is about 1/6. So this is a random phenomenon, and I'm trying to kind of motivate what a probability is. Again, if we do a ton of repeated sampling, a bunch of repeated rolls of the die, what is the proportion going to approach? And here it looks like it's approaching 1/6. Kind of makes sense, don't you think? 1/6 chance of every single number. We'll get to that in a second. Don't want to get ahead of myself. So another example of a random phenomenon. A standard deck of cards looks like the following. So, oh goodness. So I don't know how many card sharks there are in the class, but there are 52 cards in a deck. They have values, which you see in the columns, which are ace, 2 through 10, and then the face cards, jack, queen, king. And then there are 4 different suits. I hope we're all at least somewhat familiar with the deck of cards. The question I want to ask is say we are interested in how often over the long term dealing two cards at random leads to two identical cards. And I'm going to do an IE, so in other words, what is the probability, right? Proportion over the long term, probability, these are the same idea. That two cards drawn randomly are the same, ignoring the suit. So what's the probability I get two eights, two aces, two kings, et cetera, et cetera? There are two ways to answer this question. Okay, the first is empirically. The idea here is you just repeat the experiment many times and record the proportion of successes. If a probability is the proportion if we did the proportion of times we get a success if we did an infinite amount of times, well, let's just do it a huge amount of times and that'll be a good guess of what our probability is the idea. So in our example of trying to see what is the probability of drawing two cards giving us two identical cards, to do the empirical solution, we say we drew two cards from a shuffled deck – 16,000 times. And 963 times they matched. This happened, we would estimate the probability as 963 out of the total 16,000, which is approximately 0.0602. So if you wanted the empirical estimate of what the probability of getting two cards, drawing two cards that match, it would be this. You would do it a bunch of times, you would record the proportion, and that's your best guess, the empirical solution. The other possible solution is a theoretical solution. And what we do here is we assume every card is equally likely to be picked. And from this assumption, we figure things out logically. So in this example, I'm going to give you an example of how I would solve this using a theoretical solution. So say we draw one card. So we draw a first card, and it's the 8 of hearts. Then the probability of me, did I say you? Yeah, we. The probability that we draw another 8, again, assuming that all possible cards are equally likely to be drawn, is just 3 over 51. So this is the number of cards left in the deck after taking out the 8. And this is the number of 8s left. And this is approximately 0.05882. Now, since this is the same calculation, no matter which card I picked first, our estimate for the probability is 0.582. So didn't matter. It didn't actually matter if I picked the 8 of hearts or if I picked the king of spades or if I picked the 2 of diamonds. No matter which card I picked first, the proportion of the time my next pick is the same card is 3 out of 51. So if that's a bit of a leap for you after class, try to think about it a bit more and maybe come and talk to me. But this is an example of a theoretical solution. And note 2 things. Note first that the values are different. These 2 approaches gave us different values, although very much they're in the same ballpark. This one, the assumption for the empirical is that we can take a very, very large amount of draws and use that to estimate what would happen if we had an infinite amount of draws, right? So that one has a little bit off to it, right? And the assumption on the theoretical one is right here, that every card is equally likely to be picked. Is that actually true? I don't know. But this solution, the theoretical solution, is only true if that is true first. So each of them have their shortcomings and their advantages, right? The empirical solution didn't need to make any assumptions whatsoever, but it is an estimate, whereas the theoretical solution had to make this assumption that every card is equally likely to be picked. So these are the 2 ways that we want to try to get solutions when we ask questions about random phenomenon. Any questions on this? Okay. Next thing I want to talk about is probability distributions. And talking about probability distributions will be useful for us because it kind of gives you a framework of a good way to approach problems like this, a good way to approach problems in probability. Okay. So in the same way as a distribution was all possible outcomes and how often those outcomes happen, probability distribution is just a slight extension to that. It is all possible outcomes and the probability of each of these outcomes. So this is the idea of a probability distribution. And I want to motivate it from here on out. When we talk about probability distributions, we're usually talking about theoretical probabilities. So we're going to make some sort of assumption, usually everything's equally likely, and then we're going to kind of figure out what the theoretical probability is for the things that we are about to speak. About which we are about to speak? No, that was a bad sentence, I apologize. So there are 3 steps with defining a probability distribution. And I'm going to explain each of these steps by means of an example. First step is pretty straightforward. Describe a random phenomenon. So I'm going to show you how to do this with an example. So I am going to use the example of tossing a fair coin. So my random phenomenon can be described by saying toss a fair coin 4 times and note the outcome. Heads or tails, in order. So note if it was like heads, heads, tails, or tails, heads, heads kind of thing. All right, so this is the first step with probability distributions. You want to start by just defining what your random object is. 2, you want to describe all possible outcomes. So what could happen? We could get 4 tails in a row. We could get 1 heads and 3 tails, and here are the different possible ways we could get that. Right? We could get 2 heads and 2 tails. Ah, ah, ah. We could get 3 heads and 1 tail. And we could get 4 heads. Ooh, no, I'm forgetting one. Am I forgetting one? No, that's good. 4 heads. So this is every single possible thing that could happen if we were to flip a coin 4 times and record heads or tails and in what order. And what we call this is the sample space. Okay? Or S. So the sample space is the set of every single possible thing that can happen. So whenever you have a random phenomenon, define it and then think about what all of the different combinations of things that could go on. In this case, there are actually 16. Outcomes here. All right, so that is describe all possible outcomes. The third and final step is assign a probability. to each outcome. So, since the coin was fair, and there are 16 total outcomes, we'll assume that each outcome has probability 1/16. Okay? So we have successfully defined a probability distribution. We have outlined every single possible outcome, and we've given every single outcome a probability. We think they each happen with a 1/16 probability. Okay? Any questions on this? So we have another definition. An event is an outcome or set of outcomes in other words, it is a subset of the sample space. So I'll motivate this with an example. What's the probability of the event that we observe three heads and one tail in any order? So note, three heads and one tail, that is not a singular value in our probability distribution. That in fact is a group of values. No, three heads and one tail. In fact, that is a group of values. That's these four right here. We aren't referring to a single outcome. We are in fact referring to a whole set of outcomes. We're referring to an event. So in this case, our event, I'm going to call it event A, or the shorthand, sometimes we just give it a variable. So A, the event A, is equal to this set of outcomes. Okay? So rather than singular outcomes, we now have a set of outcomes, and the question is, what is the probability of A? I'll tell you. So, since each outcome in this subset happens with probability 1/16. The probability of the event is just the sum of the probabilities of the outcomes. So in this case, we have probability of heads, 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 tails, which is 1/16, probability of heads, heads, tails, heads, 1/16, and so on and so forth. We just add up the probabilities of every outcome in the event, which means to get 1/4. So what we would say is event A happens 1/4 of the time. If I were to flip a coin 4 times and record the number of heads and tails, 1/4 of the time I would get, what was it, 3 heads and 1 tail. Make sense? Cool. Yeah. So, wow. We've actually finished a little bit early. This is up until where I got with my last class, which is totally fine. So what I think I'm going to do is the video lecture is posted. Your homework is posted at 4:30 as usual. I might just hang out. If any of you have any other questions about the exam or on this lecture, you can leave if you would like. But if not, maybe I'll just open up this last 10 minutes of my time as office hours. So thanks, everyone.